this presentation will be recorded and put in the cloud. All right. Welcome, everyone. This is our first Physics Journal Club meeting of the semester 2021. And today we are very, very much excited to have Herlik Wibowo. He's a former PhD student here at Western. He did his both bachelor's and master's in Indonesia, and now is a postdoc in Taiwan. And so he'll talk to us about density functional theorems and Kohn-Sham problem. And so if you got a chance to look at the paper, I would like to just mention that the Physics Journal Club, it's just about getting the main ideas. And if you're interested to go into details, you can always contact the speaker and get that conversation flowing. All right, and so now without any further ado, let me hand it over to Herlik. Herlik, go ahead.
Okay, thank you very much for the introductions. First of all, of course, I would like to thank the organizer of our Western Michigan University Physics Journal Club for giving me an opportunity to present a paper entitled First Step in the Nuclear Inverse Kohn-Sham Problem, from Densities to Potential. Oops. What happened here? Oh, I cannot move my slide. Okay, let me sharing again. We have tried this before. I don't know why. Okay, very good. Now, sorry about a little bit delay. So this is the list of the authors. So from the name of the institute and the place, we usually refer them as Milano groups. So actually, this paper, this work is based on the master thesis of the first author, which is Giacomo Accorto. So if you like to learn further or more about this work, you can always learn from his master thesis. What happened here? Okay, so the outline of my talk today is as follows. First, I will give you an introduction to the density functional theory.
Sorry,
and I will end. Yes.
We can't see your slides.
Oh, you cannot see my slide?
Yeah.
Oh, okay. Now you can see my slide, right?
Yes, it's all good.
Yes. Okay, so the outline of my talk is as follows. First, I will give you some introduction to the density functional theory. And after that, in the end of the introduction, I will define what is the Kohn-Sham problem and what is, of course, the inverse Kohn-Sham problem. After defining what is the inverse Kohn-Sham problem, we will discuss the two inversion methods to solve this inverse Kohn-Sham problem, which are suggested by the authors, which are Van Leeuwen and Behrens methods, and constraint variational or CV methods. And after that, we will learn how the authors implement both methods to solve the inverse Kohn-Sham problem, where the target densities first coming from the Hartree-Fock calculations, and after that coming from the experiments. And in the end, of course, there will be conclusions and perspective. Okay, let us start with the introduction to the density functional theory. We usually start with the Hamiltonian of quantum many-body system. of interacting particle under the influence of an external potential. So basically, this Hamiltonian of a quantum many-body system contains three terms. The first term is the kinetic energy operators. The second term is the two particle interactions operators, and the third term are related to the external potential acting on the particle density. So we usually want to know or wants to determine what is the ground state energy of the system. We usually, in the quantum mechanics, we can calculate the ground state energy of the system from the sandwich of this Hamiltonian of quantum many-body system with respect to the ground state of the many-body system. Here, our rho naught represents the ground state density. So the density functional theory actually was built from the two fundamental theorem or one fundamental theorems coming from Pierre Hohenberg and Walter Kohn. They call the theorem called the Hohenberg-Kohn theorem. The first Hohenberg-Kohn theorem actually tells us that a quantum many-body system of interacting particles under the influence of an external potential, the ground state of density uniquely determines within a trivial additive constant the external potential acting on the density. So actually, the first Hohenberg-Kohn theorem tells us that there is a one-to-one correspondence between the ground state density and the external potentials. Okay. Let's save again. So therefore, because of this one-to-one correspondence, we can write the total energy, ground state energy of the system as the functional of the ground state density. The first two terms here, which is the functional, the kinetic energy and the two particle interaction functional, can actually is universally valid. Therefore, we can collect them into one quantities named the Hohenberg-Kohn universal functionals.
Hey, Herlik, I think you're sharing the wrong screen.
Huh?
We're looking at your web browsing history here.
Oh, no.
Yeah,
oh, really?
It's riveting.
No, I'm seeing the slides.
I see the
Alright.
slides too.
Are you really? Wow.
Yeah.
Weird. Okay.
Who can that be?
I see them now. So, all right.
Okay.
Oh, there's a lag, maybe.
There must be a lag.
Yeah. So is everybody seeing my slide now?
Yes.
Yes.
I
Yeah.
Okay. Okay.
Yeah.
Right. So the second Hohenberg-Kohn theorem actually guides us on how to determine the ground state density. To summarize, it's actually easy. It's a ground state density, actually the density that minimizes this energy density functional. That's it. So now we can see that how this density functional theory get its name. So from these two Hohenberg-Kohn theorem, we can define the density functional theory is actually an approach to solve the Schrödinger equation of the many-body system based on the concept that energy is a functional of the density. The Hohenberg-Kohn theorem actually implicitly assumes that the ground state density is a non-degenerate. Non-degenerate. To lift this, the criteria or the requirement of the non-degeneracy, we actually can we usually use what we call a Levy constraint search definitions of this Hohenberg-Kohn universal functionals. It actually says that if there is a set of anti-symmetric many-body wave function which gives us the ground state density, the true ground state many-body wave function is the one who minimizes the expectation value of these two operators, the kinetic energy and the two particle interaction operators. Therefore, actually the ground state energy can be determined via these two minimization procedure. The first minimization procedure coming from the density, and the second one coming from the many-body wave function. So there is an advantage and disadvantage using the density functional theory. The first advantage is related to the number of variables that we have to deal with. For the n-body system, we actually have to deal with a complex wave function with 3n variables. But when we use a density functional theory, we just need to deal with a real function with the 3 variables. If our system is spherically symmetric system, the things get better because we can the problem reduced to the problem of 1 variables, which is radial variables. So the disadvantage of this density functional theory coming from the fact that the first Hohenberg-Kohn theorem actually just predict the existence of the universal functional, but it doesn't give us any clue or provide us any clue how to build this functional. Nevertheless, Walter Hahn himself got a Nobel Prize in chemistry, not in physics, in 1998 for his work of the development of the density functional theory. So the basic of the density functional theory that I just discussed is actually meant for the electronic system. For the nuclear system, which is isolated self-bound system, that we need to introduce, we need to make some modifications. The first one, we need to use the center of mass frame coordinates instead of the laboratory coordinates. And we need to replace this ground state laboratory density, the rho naught that I mentioned before, with the ground state internal density, which is the density relative to the center of mass of the system. And to facilitate the proof of this Hohenberg-Kohn theorem, we need to introduce the auxiliary potential. Why? Because for the electronic system consists of the atomic nucleus and the electrons. Between 2 electrons, there will be like a there will be repulsive Coulomb interactions. To have a bound system, it means that we need to have another interaction, which is attractive interaction. In the electronic system, it is provided by the positive ion or the atomic nucleus. So this attractive potential to bound these repulsive interactions, we call it external potential. But for the self-bound system, the whole system is already attractive. It means that the self-bound system doesn't need any external potential. And as we saw before, that the first Hohenberg-Kohn theorem depend on this external potential. Therefore, to facilitate this proof of the Hohenberg-Kohn theorem for the self-bound system, we need the auxiliary potential. So therefore, the energy density functional can be written like this. And the last term is actually the term for this auxiliary potential. I invite you to learn more about this by reading the paper, the work of Massoud, Bender, and Surov. So, because we don't know how to build the Hohenberg universal functional, actually it is very hard to solve the density functional theory. It is very hard to use this density functional theory. However, in 1965, Walter Hahn and his postdoctoral researcher, his name is Lu Jiu-Sam, they come out with an idea that to introduce a fictitious, non-interacting non-interacting single particle orbitals. So they can use these non-interacting single particle orbitals to build the ground state of the many-body system. So in terms of these Kohn-Sham orbitals, or the single particle orbitals, they can define what is the non-interacting kinetic energy, and also they can define what is the heart rate energy. Therefore, now our energy density functional contains, besides of a part of these two terms, it contains another two terms. The last terms coming from the related to the auxiliary potential, because we approach or we approximate the system of the interacting particle with the non-interacting single particle orbitals, there is many body effects or correlation that left out. This effect of this correlation that left out and the exchange correlation effect that left out is taken into account by these new terms. We call this exchange correlations energy functional. So we can minimize this energy density functional with the constraint that we require our single particle orbitals to be normalized. And finally, we will get very similar with the Schrödinger equation, the internal Kohn-Sham equations. Here, the VKS is the Kohn-Sham potential, and this Kohn-Sham potential actually consists of these three parts. The delta here just the symbolic represents the functional derivative. Now, in the paper, actually, the author writes the Kohn-Sham equations in the equation 3, but I just want you to keep in mind that the density that they meant was the internal density instead of the laboratory density. And now we can define what is the Kohn-Sham problem. The Kohn-Sham problem is about from once you have your Kohn-Sham potential, you can solve your the Kohn-Sham equations to get the Kohn-Sham orbitals, the Phi here. And from this Phi, you can calculate what is the ground state density. The inverse Kohn-Sham problem actually the other way around. The ground state density usually in the nuclear experiment can be measured. It means that we can know what is our nuclear density. From this nuclear density, we want to know what is the Kohn-Sham potential. We want to solve this Kohn-Sham equation to get the Kohn-Sham potential. So this is we name the name of this problem is inverse Kohn-Sham problem. So according to the author, according to the paper, there are at least two methods to solve this inverse Kohn-Sham problem. First, the van Leeuwen-Barré methods and the constraint variational methods. What are they? Now let's see. First, let us talk about the VLB methods. Actually, this VLB method is an iterative procedure. The algorithm is quite simple. As an input, we have a target density, rho tilde, and the trial potential. From the trial potential, we can solve what is the spherically symmetric Kohn-Sham equations to get our Kohn-Sham orbitals. And we can, from these Kohn-Sham orbitals, we can calculate the radial density. And from this radial density and the target density that we already have in hand, we can calculate what is the next potential using this recurrence relation. After that, we need to check the convergence condition, which is the variation, the absolute variation of the potential have to be below a certain value. Here, the author actually gives the value is 20 keV. If it is a yes, means that we already get our Kohn-Sham potential. If it is a no, then we can we have to recalculate the Kohn-Sham orbitals, and after that repeat the whole process until the convergence is achieved. So different from the VLB method, in the constraint variational method, we start with the cost functional. What is a cost functional? The cost functional consists of the objective functional, which is the kinetic energy of the non-interacting orbitals. And we minimize this objective functional with two constraints. The first coming from the requirement that the density has to be the same as the target density. We call it a density constraint. The second one coming from the requirement that our single particle orbital has to be normalized, and we call it an orthonormality constraint. Although it seems that we start with the different quantity, we still talking about the Kohn-Sham equation here, because if we substitute this cost functional into the Euler-Lagrange equation, we actually come back to the Kohn-Sham equation. So this is basically solving the same problem with different language, which is the variational language. So the algorithm is the inputs now a little bit different. The inputs now is the target density and the trial orbital, and of course the cost functional. And after that, we need to rescale. We need to scale these trial orbitals, and we get the rescale orbitals, which is we denote here as F. After that, the author used the nonlinear optimization library. The name is interior point optimizer, where there are two the convergence conditions coming from the constraints G and the rescale orbital F. From this procedure, we obtain the rescale Kohn-Sham orbital, and we come back to the Euler-Lagrange equation, which is actually the differential equation in F, where the Lagrange multiplier U and the epsilon ij, which is the energy, are the unknowns. We can solve this the system of linear equation numerically to finally get our Kohn-Sham equation. After describing these two different inversion methods, now let us see how the authors implement these methods in the calculation using the target density coming from the Hartree-Fock calculation. So the Hartree-Fock calculation here using the ascertained force or interaction. The name of the interaction is a SCUM X. If you want to learn what is this interaction, you can refer to the paper of the Alex Brown, written here. And the author calculate implement these methods to the two doubly magic nuclei, which is calcium-40 and lead-208. And this is the first result that they present. The figure in the left is the radial density for neutron and proton for calcium-40, and in the right is for lead-208. The upper panel and the lower panel for each figure, from each figure, actually, they are describing the same quantities, but in the different scale. The upper level in the linear scale and the lower level actually in the logarithmic scale. So from these two figures, we can see that the VLB and the CV methods actually reproduce the radial density very well, which is coming from the Hartree-Fock calculations. But if we compare the maximum and the average differences between these two densities, between VLB and CV methods, we can see that the maximum and the average differences for the CV methods usually smaller than the VLB methods. The author argues that this demonstrates that the convergent conditions of the CV methods is actually very strict, more restricted than the VLB methods. So after comparing the density, the author also comparing the obtained Kohn-Sham orbitals. The upper figure is for the calcium-40 and the lower figure for the lead-208. And the upper panel for each figure is describing the delta U, which is the difference between the Kohn-Sham potential coming from the two inversion methods and coming from the Hartree-Fock calculations. We can see that actually these two inversion methods reproduce very well the Kohn-Sham potential, which is in agreement with the the one coming from the Hartree-Fock calculation, but the delta U for the CV methods usually smaller than VLB methods. And finally, the last figure, the next figure that the authors saw us, the authors want us to believe that the convergence of the Kohn-Sham potential, because as the author saw here, that the variation or the absolute variation of this potential actually become decreasing when the number of iteration is increasing. It means that it basically converges. After comparing the result from the other numerical calculation, which is Hartree-Fock calculation, the author also compare their result with the experimental densities. For the experimental densities, actually, for proton densities of the calcium-40 and lead-208, it comes from the electron scattering data. But for the neutron density for lead-208 is coming from the proton scattering measurement. I'm not really familiar with this experiment, but the author mentioned that when they extract these target densities, they use the parameterization based on a sum of the Gaussian function. So the author shows that at least for the calcium-40, the two inversion methods again reproduce very well the target densities, but there is a problem with the Kohn-Sham potential that the Kohn-Sham potential obtained from these two inversion methods. The problem which can be seen here is in the asymptotic region, which is very quite large R, or the interior of the nucleus, that the behavior of the potential, the Kohn-Sham potential, the obtained Kohn-Sham potential actually very very wild, very bad, which is it can be keep increasing with no limits. And as we see the delta U in the upper panels, we can see that the delta U actually increasing in the exterior of the nucleus. Again, when comparing between the maximum and the average differences between target density and the Kohn-Sham density, we always see that the CV methods give the smaller values of both quantities. And the same also can be seen for the lead-208. Okay, now we end our discussion with the conclusions and perspective from the authors. The authors have applied the inversion methods, VLB and CV, in calcium-40 and lead-208. The Kohn-Sham potential actually was obtained from these two inversion methods is in a good agreement with the one obtained from the Hartree-Fock potential. However, when the authors compare the result with the experimental target density, they saw that in the tail of the Kohn-Sham potential, the behavior is not very good. That's coming from the fact that the problem coming from the tail of the Gaussian function, the tail of the Gaussian density. So the author mentioned that give us some perspective about his work, that the nuclear energy density functional actually is not so easy because it depends on the gradient of the density, spin densities, and their combination, which cannot be deduced from experiment. It means we need to rely from other calculation, which is ab initio calculations. And there is no guarantee that a purely local effective potential is a correct choice, because we also know that the non-local energy density functional also work very well in nuclear physics. And finally, the extracting an effective potential from inverse Kohn-Sham problem actually is not enough to determine the energy density functional itself. I think that's it that I want to share from you. So I would be happy to answer your questions. Thank you for your attention. Hello?
Yes, yes. Thank you very much, Herlik, for an amazing presentation. Yes, I'm sure. Yeah, I see everybody is also clapping, or others haven't figured out to the clapping button. Yeah, thank you. I'll hand it over to Elena to sort of lead the discussions and questions and
I
anything.
just stop sharing first so that I can see others. Yes, but I need to share again. But later on, yeah.
Thanks for the talk. It was actually a very nice summary of what we know, more or less, on the nuclear density functional. So questions, please.
I saw very new names. Hi, Kyle. Hi, Donna.
So,
It was too clear that there's no questions.
So I have two questions.
Yes, yes.
go ahead.
So first of all, you explained that in nuclear density functional theory we use center of mass system instead of lab system. So why do we do that? And did you get my first question?
Yes, yes.
Yeah.
Actually, okay, yeah. So laboratory density means that we have a fixed center of coordinates, which is in the electronic system. The center of mass of the atomic nucleus actually quite fixed because it doesn't move, right? We always refer that the nucleus is quite heavy and it doesn't really move so much, so that we can actually put it as a center of coordinates that we can use. That's the laboratory density, laboratory coordinates. However, in the nuclear system, you know, it's part of the nucleon. They are moving around, and it means that the center of mass actually they are moving around. So it means that the laboratory density actually becomes zero, so that it doesn't make sense to use the laboratory density instead of this internal density. So that's why we need to change we need to shift from the laboratory density to the internal density. And actually, according to some other authors, they mentioned that actually the density that is the densities that are probed in the experiment is internal density, is not the laboratory density.
Yeah, because I've always seen these systems in the collision. I did not think of nucleus as a.
Yeah, me too. If I don't give this talk, I will not think about it. So yeah.
So yeah, the second question is that you explained in the VLB method we have a trial, we use a trial potential.
Yes, yes.
So how do we predict the trial potential? How do we start the prediction?
Usually we have a favorite potential in the nuclear physics that we use as a trial potential. We like to use something that's very similar to the one that we know from the experiment, right? So the name of this potential is a Wood section potential. So you can use Wood section potential, or you can use the harmonic oscillator potential. So I think in the if you read the thesis of the first author, he actually used several potential as a trial potential. Yeah. So this is how usually we use potentials in a trial potential in the calculations. Yeah.
Okay, thanks a lot.
Yeah. No problem.
Yeah, I also had like a very tiny question. If you go back to the slide
Sure.
where you talked about the changes that we have to change from the lab frame of reference, and there was something about raw internal, and I wasn't sure if.
I think it is better for me to.
Yeah.
Okay, I think this one, right? You talk about this.
Yeah.
Okay.
That internal density. Yeah. What did you mean by that?
Internal density is a density relative to the center of mass of the system. Yeah. Of the nucleus. Yeah. Of the atomic nucleus.
Okay. And the Okay, I wasn't sure what the auxiliary potentials, what are they supposed to do?
Okay, it's a good question, but yeah, again, if you in the electronic system, right? In the electronic system, you have an atomic nucleus and you have an electron that they have their own interaction, right? So between this electron, these two electrons, the interaction is the repulsive interactions. This is like a repulsive Coulomb interaction. But you want to have a bound system, right? You cannot have just a repulsive interaction. It means that they will go away, they will collapse, right? So it means that you need another interaction that hold these repulsive interactions together, right? So this attractive potential, it has to be attractive potential. This coming from the atomic nucleus. So the language we use, this is as the interaction that is provided by this atomic nucleus, we call it an external potential. It means that external potential has to be there to be able to create a bound system. But if you have a nuclear system, when you have a nuclear system, you basically don't care about the electrons, right? You just care about the interaction between the nucleons. The fact that the atomic nucleus, they are a bound system, it means that the interaction between these nucleons is already attractive. It's already it's already capable to build a bound system. But if we come back to the first Hohenberg-Hahn theorem, we need the kind of like an external potential to prove the one-to-one correspondence with the density, right?
Mm-hmm.
But in the self-bound system, we don't have this external potential. That's why we need to introduce another potential. We call it the auxiliary potential. This auxiliary potential, in the end, you can just drop it.
Okay.
And this auxiliary potential is actually, they are written in the center of mass frame coordinates. It means that they will not like affect your the whole separation between the center mass coordinate and the relative coordinate that we usually use in the many body problem, right? Yeah, like in the two body problem, you remember in the quantum one, we usually separate our coordinate into the center of mass coordinate, which is we usually use like R1 plus R2 divided by 2, something like that.
Yeah.
And also there is another coordinate, right? Relative coordinates.
Yeah. Mm-hmm.
So yeah, so basically that's what we are doing right now. Yeah, but this is very long discussion. That's why if you want to learn more about this, I always invite you to read this paper of these persons, Masood, Bender, and Surot. Is quite clear, very clear, I think. Yeah, to explain. They start with the separation of the center mass coordinates and this relative coordinate and so on. Yeah.
Yeah.
I hope I answer your questions, but yeah.
No, you did. It's really quite interesting. And yeah, I think it was what I liked in your presentation is also the transition from the electronic system to the nuclear system and the caveats that we face. I think that was really good. Thank you.
Yeah, thank you.
Other questions, please? Maybe I can ask.
Okay. Sure.
If you allow.
Yeah, of course, yeah. Because if I cannot answer it, you will answer by yourself, maybe.
I'm not sure. So the
Okay.
theorem states that if you have, can you just go back to the foundation of the theorem? So it says, as far as I remember, in this context.
Oh yeah, that's one.
If you know the ground state density, then you can restore. Yeah, if you know, wait. Yeah, if you know the ground state density, I'm talking about the first 3 lines.
Yeah.
then you can uniquely determine the external potential, right?
Yeah, yeah.
So that's okay for electronic systems, because this potential is formed by the nuclei, right? So if you go to self-bound, because I'm more interested in the self-bound case, this external potential that you put is auxiliary potential. It's a fictitious
Yes.
potential that you use basically. Well, I think technically what we do, if you do Abel-Nizar calculations, we put some potential in the one-Borda Hamiltonian, because then you can determine the basis which diagonalizes the free Hamiltonian plus this auxiliary potential, and then you can use this as working basis. But then in the end, you can eliminate. You have to eliminate this, right? So if this is fictitious potential, what's the point of Kohn-Berg-Kohn theorem? I mean, what do you determine? You determine fictitious potential. And what's the point of this?
Well, the first
Determine that you determine something that you don't need in the end. That's my question.
Yeah, but the things like if you don't have this auxiliary potential, you cannot justify the statement that your ground state energy is the functional of density, because there is no way that the center of the quantity here is the ground state density, which is justified if you have an auxiliary potential, I guess. Yeah. So if you don't have this, I don't think you will be able. You have a justification to write this energy of ground state energy of a system as a functional of the density. I don't think. Yeah.
I agree on that. My question is different. My question is, according to this, you can, from the density, you can determine your auxiliary potential, right? Is this correct?
Okay. Yeah. Yeah.
But this auxiliary potential is something fictitious which has nothing to do with the reality. So what's the point of doing it? It's just a general common sense question.
I think it's so that mathematicians sleep better at night.
Or maybe it can be reformulated in some different way.
No. I just. Yeah. I didn't think about it, but I just think that because we need to justify the use of this DFT in the nuclear system. That's why you need to have a proof about this. And in the end, actually, we are usually more interesting in this Kohn-Sham equation, where the whole things actually can be just written as a one potential, which is Kohn-Sham potential. And although we have this auxiliary potential, I don't know. I don't think I answered your question actually. Yeah, I cannot. I don't know. Yeah.
So we have more questions.
Yeah.
Thank you. So in the interest of time, we have two more things. One is the quiz, which is a book prize quiz, and then the other one is to present student opportunities. That's where you can get engaged. Khushi will be helpful with that. If I don't know if anybody else had one burning question, they can go ahead and ask, or we can head over. And the quiz is only should take 5 minutes. If you can't solve it in 5 minutes, don't worry. You know, it's optional. Anybody can participate, but only the grad students can win the prize. or the physics students, sorry, even if you are undergrad, you can still win the prize. Okay, so it will take 5 minutes. I'll send the link in the chat, and after that, we can then hand it over to Khushi with the grad student opportunities. Are you guys ready? Okay, everybody got the quiz questions? You can just do a thumbs up if you have it. Thumbs up if you have it. It's only 5 questions. Okay, Dave have it, Abby have it. Okay. Everybody has it. Hansaka, Khushi, Om.
What is Om?
Okay, Om has it. Okay.
Oh, okay. This one, Om. Yeah.
Okay. Yeah, so it's just 5 minutes. I see Herlik is smiling. You've made the quiz very interesting.
Yeah, yeah.
I can't participate because I have the answers. So Herlik, what made you interested in this business of DFT and the inverse Kohn-Sham problem?
Well, I think this is because it is more fundamental. Because when you're dealing with this, yeah, basically, my starting point as a PhD student, I learned about this covariant density functional. It is natural to go deeper into this nuclear density functional. This is just a natural transition. And this is like a more fundamental problem, I think. Yeah, that's why we should care about it. And the fact that there is one group that dedicate their research to this attempt is very interesting.
Or the Milan?
And, yeah, the Milano group, yeah.
Mm-hmm.
And the things like, and I also choose this paper based on the fact that I can learn more about this work because the complete account of this work has already available as a master thesis. Actually, in the end, I can send you my PDF of my presentation, and I already put a lot of link. If some of you like to learn more, so you can just click and you can directly connect it to this works. Yeah.
Oh, okay.
And
Nice.
I think I also need to have something that I can share with the students if they come to me and they want a project. Yes, this would be a very good exercise for a student because also kind of like train their numerical computational skill. Yeah.
Yeah. No, it's quite interesting that no matter what you're doing in physics, one way or the other, you hit this form or this concept of you will have to do some minimization to find your solution, and so it's like a very, very common problem. And
yeah, minimization is in many areas of physics. Like the nature tells us that a lot of things has to be minimized. Like for instance, why we have in optics we have the law of reflection, right? We have the law of reflection that the incoming angle has to be the same as the outgoing angle. You know, right? So you can derive this from the requirement of minimization as well. Yeah.
Yeah.
So basically, yeah.
just another question. Does it matter the order of the minimization? Because I saw, like you mentioned, that in DFT you have double minimization. Does the order matter, whether you start minimizing with the density or start minimizing the other?
I should share the things that you mentioned so people can understand what we are talking about, right? So wait.
Oh, they are busy with the quiz.
Maybe someone is already done with the quiz, because the quiz is not that. I think they're not really hard.
Yeah,
everything in the my talk actually. Yeah. So this one, right?
Yeah, there you go. Yeah. Mm-hmm.
So to be honest, I never do this calculation actually, but I think I cannot tell you how this actually calculate numerically. So yeah, I think the first one should be this density, because the second minimization is based on the fact that you can have a set of the antisymmetric wave many-body wave function that give you the same ground state density. So I think the ground state density has to be determined first, right? Mm-hmm. Before you you minimize this. But maybe I'm wrong. But I never do this kind of problem. But I just mentioned that if you have a situation where your ground state density is degenerate, so there is another additional minimization that you need to do. Yeah.
Okay. Okay. Thank you for that response. Okay, I see Khushi she's ready with her presentation. Do you guys need one more minute, or should we call it? Because I don't see everybody's. I see some few responses. Do you guys, if you need more time, a minute, just do thumbs up. Otherwise, we can move on to the last bit.
Just curious questions, Mankoba.
Yeah.
If everybody got perfect scores, so is everybody get the prize?
No, that would never happen. But I'm just kidding.
So if this happened, it means that I composed a very bad question, right?
Usually. But yeah, no. What if people are tying in score? What we do is just pick a random number.
Oh, okay.
Yeah, yeah. I was just kidding. That can happen. Yeah, depending on how nice the speakers are.
I hope I put a good question. It will not be a tie or something like that.
Okay. I guess everybody is done, right? Khushi, go ahead, and when you are done, I'll present the winner.
Okay, everybody, you can hear me?
Yes.
All right. So I'm going to present the student opportunities by starting.
Now you are gone. I think you are muted, Khushi, somehow.
Okay, but I can't change my slides. Let me try once.
Same here. Same here.
Yeah. Technology, it works except when it doesn't.
It works until you need it, right?
Okay,
I
think it works. All right. So initially, I'm going to present some of the funding opportunities. The first one I have is from National Academy of Education, and they have a dissertation fellowship available for grad students. For them, the deadline is October 7, but if you are a postdoctoral student, or if you are going to be one, and if you wanted to apply for fellowship for postdoctoral position, then the deadline is November 17. And I've posted several links in specific order in the chat. So the first 2 links should be corresponding to this funding opportunities. So you can pick it up from the chat. Both this funding opportunities from National Academy of Education is open for international students as well. The third one I have is from Graduate Research Fellowship Program by NSF. And for applying for this, you need to be citizen of US, but you can look it up more about it in the link that I have posted. The best part is it provides funding for masters as well as doctoral degrees. And as you see that the annual stipend is also a pretty large amount, and it is funded for more than 1 year. So the next one I have is from American Council of Learned Societies. And here again, it is for grad students. The stipend is large. And if you are interested, then look into it. The deadline is October 27. This one, I'm not sure if this will be very helpful. I did not notice it earlier. It does not require you to be American citizen by birth, but it has to be new Americans, which is some sort of citizenship related requirement. So you can look into it. It is only for grad students for pursuing a master's degree or doctoral degree in any field. The next one is from Smithsonian Scholarship, where there are several fellowship programs. There are multiple postdoctoral level funding opportunities, and I think 1 or maybe 2 graduate level funding opportunities. Deadline for grad level funding opportunities November 1. The link is again there in the chat. The next one is American Association of University Women, AAUW's International Fellowship. They have 18,000 for masters, 20,000 for doctoral, and 30,000 for postdoctoral students. This is the scholarship which I had in my first year when I came here for doing my PhD at WMU. So if you are willing to apply for this and would like to chat more about it, then you can always email it to me, or I'm available in the department. They also have dissertation fellowship, which they give for $20,000. And the deadline is November 1 for this one. For international fellowship, the deadline is November 15. So there are 2 different they offer. You can look it up more on the link that I have provided in the chat. And then the next one I have is from the Social Science Research Council. They have International Dissertation Research Fellowship available. Deadline is November 2. If you think you would like to apply for that, that one is there. And because of time constraint, I'm not adding more. But for grad students who are willing to look for research grants, you can win this opportunity 3 times. The amount could be maximum of 1,000 each time you win it, and the deadline is October 27. I've also applied and won it 3 times. So if you need any help for applying for this scholarship, you can always reach out to me. The next 3 things that I wanted to share are postdoctoral positions, mainly in the nuclear physics field. One is an Argonne National Lab in the low energy nuclear physics group with Dr. Melina Avila, where you'll be working with music detectors. The next one at Argonne National Lab is with Dr. Michael Carpenter. That is also a postdoctoral position in low energy nuclear physics research group. And the third one I have is a postdoc position in Los Alamos National Laboratory. And if you are interested, then you can probably reach out to Aaron Couture at this email address, and I think that's all I've got for now. I hope I did it in time. No, I didn't. Sorry.
No, thank you, thank you. It was just the technical difficulties that made us go extra time, but this was wonderful. And please note, I will share the, if Khushi allows, the presentation of this, so you can see it later on when I even share the recording of this video. Okay, now the moment we all been waiting for, you're the winner. It's interesting results. There are people, well, so the committee members of the PJC, even though they didn't see the questions ahead of time, we have decided we are not eligible to win the prize, but they have done very well. They've done very well. They would have won it if not for that. But otherwise, the one with the top score is Dave again. And so congratulations, Dave, for the second time. You have won it in an interesting manner. Yeah, I guess I don't know why others did not participate, because you would have, you could have won. Sorry. But yeah, congratulations, Dave. I'll send you details on how to get your book. And thank you to our speaker, Herlik. Thank you for waking up at early in the morning. Thank you,
No
Elena,
problem.
for being here. And before I let everyone go, we will have one special thing to do. Elena,
Yes.
are you there?
Here.
So today is a special day. It's Elena's birthday, and so we will we will sing happy birthday for her. And so everybody can join me. It doesn't matter who starts singing first. I think. Oh wow! Oh wow! Wow!
Just
Right
one
on time. Right on time. Okay, Khushi, do you want to help us sing? Because your voice is much better than mine. I have a cold.
Okay, I hope I am not very. If I'm not good at singing, please, I apologize in advance.
thing for you.
But happy birthday to you. Everybody do you want to unmute yourself and accompany me in singing, please?
Yes.
Yes.
Okay. Happy
Happy
birthday
birthday
to
to
you.
you.
Happy
Happy birthday
birthday to
to
you.
you.
Happy
Happy
birthday,
birthday
dear
to
Elena.
Elena.
Happy
Happy
birthday
birthday to you.
Hip, hip.
Thank you, guys. Thank you very much. This is very nice for you.
In Russian. Well,
Oh, right in
oh,
time.
hi, Dieter.
I'm only the delivery boy for the roses. No.
Oh, okay. You came right in time.
Yeah.
Nice singing, by the way.
Oh, thank you. Thank you.
Thank you.
Thank you, everyone. Have a wonderful night. We'll see you. You can hang around if you want to.